I went out there to try to find, I'm like, oh, that should be pretty cool. Let's get a video of somebody running a sample. Remember, the way this works is you burn the sample in here. It's exothermic. We talked about the term exothermic. It releases energy, and it gets this water warm. Okay, and we can get the temperature change of the water, kind of like what you guys did with your lab a week ago Tuesday, and then we know how much energy is released. But my point is that the videos were all so boring, I just couldn't take it. So we already did this slide. Okay, when we burn things, combustion is a chemical reaction with oxygen. So they say in general then, your products contain, here's your products. Your products contain oxygen. And if all you're burning is a hydrocarbon, you're going to get carbon dioxide and water. That's it. That's the only products you have. Okay, exothermic reaction. Okay. Oh yeah, we already did this slide too. So what you're looking at is these are these aren't energy diagrams, although we could do an energy diagram. In the top, we have the energy associated with the reactants that you start with, and the bottom, we have the energy associated with the products. So that difference actually is the energy released. So the greater that difference, then the more energy is released. If you're doing a bomb calorimeter, the hotter your water will get. And we're going to skip this one for now, because I just thought it was annoying. So exothermic reactions, like I brought in those, remember those, I bring the little heating pads where we know how to do that, where it gets warm. Okay. Anyway, exothermic means energy is released. So some reactions absorb energy, and instead of exo, we call them endothermic. The whole thermic, I know it sounds like temperature, you're right. So endothermic would be that they absorb energy, and what we're going to see, instead of getting hot, they get cold. So cold packs would be great if you have some sort of endothermic reaction. Looks like the word I hid down here at the bottom is the word change in energy is positive. So, you know, in chemistry, we kind of do numbers and quantities. If your energy is positive, that means it's an endothermic reaction. If your energy is negative, that means that must have been an exothermic reaction. So we can kind of think of what's going on with a diagram, with a picture. So this box right here is what we call your system. Okay? And then outside your system of interest is your surroundings, and guess what? The surroundings plus your system is equal to the whole universe. Isn't that kind of fun? Anyway, so if it's endothermic, we can go ahead and draw an arrow from energy from the outside, the surroundings, into the system. So it's endothermic, an increase in energy. That'll be a positive change. Well, exothermic would look like this. First off, the energy change would be negative, and the picture would look different. Exothermic. In this case, our system is actually giving up energy to our surroundings. That's exothermic. Well, we're going to take a look at, I think this is going to be fun, potentially. We're going to kind of count bonds, chemical bonds. So I bet you buy this, that if you break bonds, it will require energy. So the bond there, the word there is requires. Breaking bonds requires energy, whereas forming bonds releases energy. Breaking bonds requires energy, forming bonds releases energy. Kind of makes sense. There's a magical wand that you're whacking the chemical bond between two atoms. Okay, but a bond is formed, energy is released. Okay, so the word looks like I hid here is endothermic. So here in a minute we're gonna, I call counting beans. We're gonna actually count the amount of energy that's required to, like if you're in the kitchen, chop up all those atoms from each other. Okay, that's going to be energy required, and then we're going to look at the energy that's released as new bonds are formed. And if it takes more energy to break bonds than is released as bonds are formed, that's endothermic. And if More energy is released as bonds are formed compared to the energy required. When bonds are broken, then it's exothermic. Okay. So this table, looks like the words I hid here were absorbed. Bond energy is the amount of energy that must be absorbed to break a chemical bond. Actually, they will always be positive. Bond energies will be positive. And breaking bonds will always require energy. Makes sense. So here's the table. So the way you look at this is if, for instance, in carbon dioxide, which we are going to look at carbon dioxide, you're going to have to picture these things and kind of look at the table. See, the Lewis structure of carbon dioxide. Because you're going to have to know if it's a single, double, or triple bond. So, oh man, I can't remember. Let's do it right quick. Carbon is got 4 valence electrons. Oxygen, there's 2 of them. They each have 6 valence electrons from their group number. So I got 16 electrons to distribute. Let's see, I've got 4 there. So I've got 12 left over. Looks like it's going to have 2 double bonds, which some of you guys probably already remembered. Do I have 16? 2, 4, 6, 8, 10, 12, 14, 16. Okay, point here is that's the Lewis structure of carbon dioxide. In order to use this, we need to know that. Because here in a minute, when we look at how much energy is either required to break this bond, I'll just pick one of these 2, but they're the same. What you would do is look at this guy right here, 803. Okay, so it requires 803, is that kilojoules per mole? Okay, it will require it to break it, and when that bond, when that bond is formed, energy will be released in that same amount. That's how you use the table. All right. So here's where, and I didn't do this ahead of time, and I think Autumn's probably got her book, but here's where we're going to kind of do this together. Well, maybe I'll go, we'll find my book. So we're going to go around the room. You need to use the table on the previous slide. Wait, before we do this, yeah, let's do this first. All right, here goes this guy. Molecular O2 is this. Ozone is this. Okay, so we'll start with you, Natalie. How many valence electrons around an oxygen atom? You can use your periodic table. Yep. And I didn't put the I didn't put this up here. 6. She's totally right. Yeah. I need to use a permanent marker and put 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Yep, 6 valence electrons. All right. So let's knock out these Lewis structures right quick. So for 6 valence electrons, there's 2 of them here. Okay, so over to you, Autumn. Okay, so I have 12 electrons to distribute around my O2 molecule. Right now, do you remember what the Lewis structure of O2 molecule looks like? I think there is a double bond, so help me out. So if that's 4 electrons, what do I do with my other 8 electrons? Wait. Yep, that looked good. 2, 4, 6, 8, 10, 12. I'm liking it. Okay, so back to you, Glenna. So help me out with ozone. Do you remember, or can you find the Lewis structure? We have 3 oxygen atoms. They've got 6 valence electrons. So our Lewis structure is going to have 18 electrons.
Is it like 3O?
It's 3 of them, but then how do we get our 18 electrons? Do you remember?
1 double bond.
I'm liking it. I think so. And then
The rest
does that look right? 2, 4, 6, 8, 10, 12, 14, 16, 18.
Yeah.
Yep.
Give the second one.
I'm liking it. Very good. Okay. So the other part of this, one of the things we've talked about is the sun sends energy in all sorts of different radiation, all sorts of different energies. So let's see, we've got UVA, UVB, and UVC, don't we? So 320 nanometers, ozone. So incoming, I'm trying to think of a question for you, Taylor, hang on. So 320 nanometers is the wavelength. And then if you read it, it says incoming 242 nanometers is the wavelength. So Taylor, which one of those energies is more energetic, the 242 or the 320? The shorter wavelength or the longer wavelength? The shorter one. Yep. Yep. More energetic. Yep. So, Billy, look on that table that I think you have it open to. Tell me how much energy I have to zap this double bond with in order to break it.
83.
What's that?
803.
83?
803.
803 kilojoules per mole. Perfect.
498.
What's that?
498.
498? Final answer?
I think so.
Okay. So did you see where he got the 498 from, Natalie? Because I'm going to ask you a similar question. All right, Natalie. How much energy do I need to break this bond? This bond right here, between the single bond between the 2 oxygen atoms. Yeah, that one might be a weird one.
It doesn't show.
So it doesn't show down there. So this one has it, and then these are also, so you find the oxygen there and the oxygen in here, where they intersect. Yep. She's saying 146. Do you see where she got that from? 146 kilojoules of energy per mole of bonds that are broken. Very good. So Taylor said that the shorter wavelength is more energetic. This is less energy. Okay, and can you see where the bond, it just takes less energy to go ahead and break our ozone down, which that's just one of the things we talked about ozone being broken down by solar radiation, the sun's energy being compromised. Okay.
So that one, though, for ozone is going to take 146 plus 198.
Well, if you want to break it all the way down, but I was just hitting the one that was most compromised. So yeah, if you wanted to break it all the way down, but I wasn't breaking it all the way down. But this one actually, this is just an example, and I don't think I'm going to necessarily drag you through it because it's already done for you. Looks like the word I hid was breaking. So what we do in science, we do this a lot, is we compare the energies of our reactants with the energies of our products. And like I said a minute ago, if you, and then we kind of see where it shakes out with regard to, is it an endothermic reaction or an exothermic reaction? So from the table, you could find in the first part of the table where H and H is,
And you can see it's going to take 872 kilojoules per mole to break that bond. The double bond you said was 498. So in this case, what we're saying is you need to break the O2 molecule. You need to break 2 H2 molecules, or maybe I took the H2 times 2. Sorry, yeah. The single H2 from the table you see is 436 times 2 is 872. So if we add the 872 plus the 498, you get what bonds are being broken on the reactant side. Okay, on the product side, we have just water being formed. So you end up with, there's two water molecules. To me, I just gotta picture this thing. And in a given water molecule, you have 2 OH bonds. So here's our central oxygen atom, hydrogen, hydrogen. Of course, the Lewis structure looks like that. So that's why it says, and we've got 2 of these. So in one of them, you break this twice. So if you've got 2 of them, that means that actually you're going to break or form 4 of those bonds. So actually it's showing the formation of 4 of those bonds. So if you find on your sheet, you can see where the breaking is 467 kilojoules per mole, but the forming is negative 467 kilojoules per mole. So 4 times that gives us our negative 1,868 kilojoules. So if we look at the energy released when bonds are formed versus the energy taken in when bonds are broken, notice that it's a net negative. And net negatives mean that energy is released. So that's what makes it exothermic. Oh yeah, you do have one, don't you? Okay, so let's go through this one together, shall we? Let's see, I think we left off, who we leave off with? Do you remember? I think so too, so I think we're up to you, Autumn. Okay, let's see what we got going on here. So if it's going to be basically our strategy, let me go ahead and find my pen here, hopefully. Our strategy is going to be to break everything on the left side, our reactant side, and that would be positive energy, energy absorbed, and then we're going to form bonds on the product side. So these are going to be breaking, and these are going to be forming bonds. Okay, so breaking the bonds, we're going to have positive energy. That means it's endothermic. Forming the bonds, we're going to have negative energy. That means that it's exothermic. All right. Ready, set. So here's our brick wall. So help me out, Autumn. So it looks like we're going to need to break these 2, and I'm grateful for these structures because otherwise it'd be very confusing. We are breaking 2 CH bonds. Okay, how much energy is going to be required for each breaking of a CH bond?
416 times 3.
Very good. So plus 416 kilojoules. And can you go, I heard you tapping on the calculator. Can you tell me what that is? 832. Awesome. And that'll be positive. So we're back to you, Miss Glenna. How much, probably a lot, is going to take to break this single triple bond between the carbons? Is it on the bottom there? So 813 kilojoules. Okay. All right. So Taylor, looks like we're after, can you tell me about the O2s? Oh, sorry, not the O2s, the oxygen, double bond oxygen. So we have 5 of them. Wow.
498.
Whoops, double bond, not triple bond. 5 times 498, can you tell me what that is?
2,490.
2,490 kilojoules. Yowza. So, Billy, I think you got your calculator. Can you help me out and go ahead and can you add up these energies for me? These 3 energies? Do you don't have your calculator? Okay, so how about help me out on so this is our reactant side. I'll put an R for reactant. I'm going to put P for product. So, Billy, how much energy, and I think it might even be on the board behind me, maybe not. I think I erased it. How much energy is required to break just each individual oxygen double bond carbon? Or not required, how much energy is released when they're formed? So look on your, yeah. Carbon double bond oxygen. 803? Okay, cool. I'm going to go ahead and put a negative there. I'm putting negative 803 kilojoules. And the reason I'm putting negative is we're going for bonds are formed. Basically, and this is kind of one of the things maybe Autumn talked about, we're going to break all these bonds between, make individual atoms, going to be required much energy, and then we're going to form the bonds over here. And when bonds are formed, energy is released, so we go with a negative energy. Oh, did I have 2? It shouldn't be. Oh, wait a minute. So I see you, Billy, can you help me out? What should this number be? How many of those are we breaking? Or forming, excuse me. What?
8.
8. I agree. My bad. We're going with 8.
There's 4 on each side.
Right? Because there's 4 units. There's 4 units. That's what that coefficient means. It's balancing. So we have 4 units, and for each unit, each CO2 molecule, we are forming 2. So 2 times 4
There
is
should be
8.
4 of that top one too.
What's that?
The CH bond, there should be 4 of the very top one.
This guy right here? Yep. Ugh! Why'd you say that before? Okay, well, let's fix that. So, do you have a calculator, Natalie? I'll give you mine. Is it? Oh. Can you go ahead and tap out? Let's fix things up here. Actually, Natalie, can you help me? I need help. I'm going to update this. So I guess I'm back to rightfully so. Billy said no. We have this has to be 4. Sorry, people. This has to be 4 because we have 2 units. Oh, wait a minute. Can't we just double everything? Anyway, so if that's 4, then this is 4. So Natalie, what's 4 times? I can't remember my own handwriting. Is it 416?
What am I doing?
4 times 416.
1664.
Thank you. 1664.
I don't understand why it has to be 4.
It has to be 4 because we have 2 molecules of C2H2, and for 1 molecule we have 2 carbon and hydrogen bonds, and if we have 2 molecules we have 4. Do you understand what the 2 means? The 2 in front of the.
Yeah, I thought
Sweet.
that meant 2, so you used 2.
Well, the reason we need 4 of those is the same reason as we need 8 of the. Did you understand the 8 here? Did you understand the 8? No? Okay. So do we do that? Let's work on the first one. So the first one, well, first off, what this means is H, C, C, H, H, C, C, H, plus O2, 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 O2. Goes to form O, C, O, O, C, C, O, O, C
Okay.
O. Okay. O. Okay. Well, I got to finish my thought now. H2O. Okay?
Yeah, double that middle one too.
I know, I haven't finished that. I'm still updating. But it sounds like we buy this. All right. Well, I'm glad you asked. Okay, so Autumn, can you help me out? Yep, we need to double this guy, right? So we have 2 of these bonds. So can you help me out? What's 2 times 813? 1626. And I know I should be able to do that in my head, but why? And I think we're okay with this one, aren't we? The O2s.
1626.
Yeah, 1626. Thank you. Yep, thanks. Yep. Well, since we've revisited our reactants, Glenna, can you go ahead and tell me how much energy is required to break all those bonds? Can you add these 3 quantities? So I'll tell them to you. 1664 plus 1626 plus a whopping 2490.
5,780.
5,780?
Yep.
Wow, that's the energy required to break all of these bonds. Okay. Now we're almost done. Need to get on the product side. So it looks like on the product side we still need to fix our waters. So first, what do you think, Taylor? How many OH bonds are we breaking? We are breaking 4. 1, 2, 3, 4. Perfect. And can you tell me how much energy it requires? And by the way, I shouldn't have said breaking. I should say forming. We're forming these. Energy's got to be released. So we're forming these. How much energy is released when one of them forms from the table? From the table? Let's go to Billy. Billy, from the table. How much energy is released when an OH bond is formed?
464.
464?
467.
467? Thank you. Okay, Natalie, can you tell me how much energy is released when 4 of these bonds are formed? So 4 times negative 467.
1868 negative.
Very good, David. 1868? Awesome. And it looks like, Autumn, for some reason, I missed this one up here. Can you tell me what 2 times 803 is?
8 times?
Oh, 8. Thank you. That's where. Can you tell me what 8 times 803 is? Negative 803. It's a lot of energy.
Is negative 6,424.
Awesome. So another calculator one. Back to you, Glenna. What is negative 6,424 plus negative 1,868?
Negative 8,292.
292. Yay. Awesome. Oh, go back. Not dead. Whew. Okay. So Billy, I'll put under the top one, energy absorbed or required, E absorbed, and this is E released. Was there more energy absorbed or more energy released? More energy released. Yep. So what do we call it, Natalie? It starts with the letter E. They both start with the letter E. When energy is released, do we call it endothermic or exothermic?
exothermic.
We do call it exothermic, so this is exothermic, perfect. So Autumn, can you help me out? Well, let's just add these two together. So basically, you're taking 5,780 plus a negative 8,292.
Negative 2,512.
Negative 2,512. Thank you. Kilojoules. We got that from taking 5,780 plus a negative 8,292 kilojoules. Cool. Stop. We're almost done. Because our instructions were, that's how much energy is released for this balanced equation. Our instructions were what is the heat of combustion for just 1 mole? For just 1 mole of C2H2. This is 2 moles. So, Glenna, how do we get it for just 1 mole? Divided by 2. Exactly. To finish this up, we just simply take our negative 2,512 kilojoules of energy divided by 2 moles. And the way where I got that 2 was from this 2. This 2 up here. 2 moles of C2H2. So Taylor, help me out. Oh gosh. So what is negative 2512 divided by 2?
Negative 1,256 kilojoules per mole.
Yep. You got it. Autumn, can you check? It's a your turn one.
Oh, in the back?
5.13.
Yeah, oh, jeez.
So.
Yep, it's right.
So, any questions about all that?
No, this is stats.
I'll check, then I'll let you guys know. But anyway, so tomorrow, we don't meet tomorrow. Friday, when we meet, the plan is to revisit our samples and do the test. And I was telling Billy before y'all came, I don't know, I'm not really seeing the fraction separation, so I'll probably do some preliminary work with mine tomorrow. We had 3. And now we just come and we'll just jump you right in there. And then if I can't get mine to do anything, then we're gonna have to do lecture on Friday. So I just didn't want to disappoint you. So anyway, yeah, and the test is due by the end of the day next Monday, which I know is spring break, but do it before spring break. Okay. We'll see you Friday, one way or the other. I know it's early, but yeah. Hopefully you guys will cut me some slack for letting you out early. What's that? Divided by 2 because all of our work was based upon 2, not 1. We wanted it for 1 mole, and we had actually 2. Yeah, the 2 front was how many moles that moved. Okay. Yeah. So if that had been a 1, then we would be done.
It's tiny.
We need a math class. Just for that part of it.
Yeah.
Kind of a concept thing, I think.